You wrote about adding 27 and subtracting 72. Can you add 36?
Particle motion, worksheet 1, number 1. And the calculator is only for 1F. Everything else is supposed to be no calculator. We'll see. And the test is arranged a lot like this worksheet, where there's a problem statement and then a whole bunch of questions after it. Part A, find the instantaneous velocity. Okay, I can do that. I bet that was easy. 3t squared minus 24t plus 36. And at 3 seconds, so plug in 3. And is this where you were, I almost said whining, but that's kind of cruel. Complaining, concerned about calculator usage?
Yes, it was.
Let's see. 9 times 3 is 27. 24 times 3 is 72. Plus 36.
The rest of the
Oh,
to do.
I know. So hard adding numbers.
Oh my God.
27 and 36 is 63 minus 72. I'm making fun, and now I'm going to make a mistake, and you're going to laugh at me, and it will be much deserved. -9. That's right. I'll blame it on something. The answers are on the back, so I can verify at least, but I won't verify until I make a stab at it. When is the particle at rest? So rest would mean v equals 0. So I'm going to factor out a 3 and hope that it factors. Hope that the rest factors. Let's see, 6 and 2 look like good candidates. So it's at rest at 6 and 2. That's really important for total distance travel. That's the one we started with, what prompted this question. So at 2 and at 6, it's probably changing directions. So that's what I'm really concerned about, is what's going on at 2 and at 6. When is the particle moving to the right, to the left? Justify your answers. Okay, so I need a number line then. A velocity number line. And again, I don't have to go past 0. And then 2 and 6 are my sort of my critical points for position, because it might be changing directions there. So I'll try 1 and 3 and 7 as test points into velocity. Preferably the factored form, because that's easier to plug numbers into. If I plug in 1, I get negative times 3. So that's positive. If I plug in 3, I get 3 times negative times positive. So that's negative. And if I plug in 7, it's all positive. So it's moving right when v is greater than 0. So that's 0 to 2, 6 to infinity. I should reread this question, because sometimes it puts a time limit on when this is happening, but this one doesn't. So just 6 to infinity, it's moving to the right. It's moving to the left when v is less than 0, so that would be from 2 to 6. Check my answers.
You said the answers are on the page, but are you going to post anything that's like with work so we can check that? Because physics doesn't do that, and it really doesn't do that.
I will. I think I have the work for these, so I'll post it. So part C, find the displacement of the particle after 8 seconds. So displacement after 8 seconds is s of 8 minus s of 0. Oh, this is where I'd like a calculator. S of 0 I can do, because that's just 0. But S of 8, 8 cubed, that's terrible. Who assigned this worksheet? 8 cubed is 512? Or you want me to prove it to myself?
768 plus 288.
Look at you.
No, it's 768.
Oh, thank you. So I would add the positive ones first. Hopefully without making a mistake. 800 minus 768 would be 32. Yes. Part D. Find the total distance traveled during the first 8 seconds. Okay. This is where I'm have to be really concerned because things are happening at 2 and at 6. So I think the motion diagram is the easiest way to understand what's going on. You know that something's happening at 2 and 6. So you could get distance from 0 to 2, distance from 2 to 6, and distance from 6 to 8. That would be one way to do it. I think that maybe not easier because it might be longer, but I think a motion diagram will help me visualize what's going on. At 0, time equals 0, s is 0. That's an easy one. So we're starting at 0. Again, be careful. It doesn't always start at 0. There's one on the test that does not start at 0, and that messes people up because they ignore the fact that it starts at 0 or it starts at 5 or wherever it starts. Let's see. S of 8 we already found, so that was at least some consolation. So I need S of 2 and S of 6. And even if I wasn't doing a motion diagram, at some point I have to find S of 2 and S of 6. So it's not making more work on that front. 8 minus 48 plus 72. 80 minus 48 is 32. S of 6. Now I understand why you want a calculator. Forgive me for making fun of you earlier. 6 cubed is 216. 12 times 36, I don't know. Plus 36 times 6. Let's see. I'm gonna use a math property there. Rather than multiply 12 and 36 and 6 and 36, I'm going to say that I'm going to hold the 36. Negative 12 of them plus 6 of them is negative 6 of them. And 6 times 36 is 216. So actually S of 6 turns out to be 0. I used the distributive kind of property there. It's like I had negative 12a plus 6a is negative 6a, but a happens to be 36. Rather than have to multiply both of those, that out and that out, I did an algebra step first. So time equals 0, we're at 0. Time equals 2, we're over at 32. And I'm also checking this against my velocity picture. Velocity was positive from 0 to 2, so this makes sense. Velocity was negative from 2 to 6. And then velocity is positive from then on. At t equals 8, we're back at 32. So total distance from 0 to 8. 32 plus 32 plus 32 equals 96, whatever units we're in, meters. So again, you can do that without the motion diagram, but I think the motion diagram really helps clarify, explain how to find the total distance. Keep going. Part E, find the acceleration of the particle. Well, that would be the derivative of velocity. So that would be 6t minus 24. And at time 3, A3 equals 18 minus 24, negative 6. Part F, oh, I should have told you to skip part F. Although it says use a calculator, so you would just put them in the calculator and look at them. So you skip it or not, don't skip it. All you're doing is looking at a graph on the calculator. But when you look at all three at once, I don't think it's helpful. If you look at them one at a time, maybe it's helpful to see what's going on. I think the motion diagram is the most helpful picture to look at. Part G, speeding up, slowing down. Okay, so I need a velocity and an acceleration chart. The overlapping charts. Velocity we already did. That was 2 and 6 were the key points. And it was positive, negative, positive. What's going to be a key point for acceleration? Set it equal to 0. So at 4, let's see, less than 4. So if I plug in something less than 4, I get negative. If I plug in something greater than 4, I get positive. This is why I like to put lots of symbols on there, because some people are fine using this. Where do they have the same sign? Where do they have opposite sign? For me, it's if you put a whole bunch of symbols on there, I think it's easier to see, when they have the same and when they have different. But that's not necessary at all. So from 0 to 2, let's see, they are fighting each other. So it's slowing from 0 to 2. And from 4 to 6.
What did you plug in, for the A line, for the acceleration line? How did you know if it was positive or negative?
I plugged in something less than 4
Into that?
into that, anything less than 4 versus anything more than 4. Speeding up when the signs match, so that would be 2 to 4, and 6 and on, 6 to infinity. So 5, C, and D. Let's see. Let's make sure I know what graph I'm looking at here. The figure on the right shows the position of a particle moving on a horizontal line. So position S. It doesn't want me to get confused on what graph I'm looking at. Graph the particle's velocity. Well, velocity is derivative of position. So the slope of the position graph. If it doesn't specify, you could graph it on this graph or you could graph it separately. I graphed the last one on the same graph. Some people that throws them off. So on this graph, I'll graph it on a separate one. You're welcome to graph it on the same graph if you can keep it straight and be careful. But I'll graph it on a separate one on this one. It's a matter of can your brain handle two graphs on one axis. Let's see, from 0 to 1, the slope is, careful. Without any numbers, it looks like the slope is 1, but with numbers on there, the slope is 2. 0 to 1, velocity is 2. From 1 to 2, the slope is 0. From 2 to 3, the slope is negative 4. So from 2 to 3, the slope is negative 4. From 3 to 5, the slope is 0. And from 5 to 6, the slope is negative 2. And again, if you really wanted to put that on the same graph, you could have, but maybe it gets confusing. All right, graph of acceleration. A different color for acceleration. That's the slope of velocity. Now, let's get real technical here, because those should be open circles on all those, because those are cusps, so they don't have a velocity at those points. Just going to make my acceleration graph, I don't know, in some ways easy, in some ways not easy. What's the slope of all of those little pieces? Of each individual piece? 0. So my acceleration is always 0 except where it's not defined. So this is a little bit weird. At 1 and at 2 and at 3, 4 we're good. At 5 and at 6. So when it's defined, it's 0. When it's not defined, I can't really say anything. We can think of that as there's these abrupt changes of velocity. Well, you can't. That doesn't make sense. Like, there's not a derivative at 2. There's not a derivative at 3. Like, there's a jump there. So, yeah, it's 0 when it exists. Yeah, it was probably a good idea to put those on a separate graph. Otherwise, 2 graphs on one, okay, you can kind of make sense of. If you put all 3 of those on one, that's a little bit much. Especially since from 3 to 5, they're right on top of each other, so you could probably separate that up. Are you okay with ones like the calculator ones, like number 4? Just using, I mean, it's really, do you know how to use the calculator? I think the calculus is that hard. Well, I'm going to pretend that somebody asked number 4, because we haven't done a whole lot with the calculator. So, number 4. Its velocity is given by that. What is the acceleration at time 4? So how is the acceleration related to the velocity? It's the derivative. Now, I've got a calculator, so yes, I know how to take that derivative by hand, but it tells me to use a calculator, so I'm going to type in the velocity. 3 plus 4.1 cosine 0.9x. Always in radians in here. In calculus will always be in radians, so that's a difference between physics. Physics, you're a lot of the times in degrees. Maybe most of the time in degrees. Let's see, I don't know if this is a good scale or not, but we'll just try it. So how do I use my calculator to find the derivative of that graph? Do you know where it's located? You want to do some calculus? Second calc? dy dx? And then you can use the scrolls or like left and right arrows, or you can just type in time equals 4. And dy dx is 1.633. So that's an easy question if you understand that acceleration is derivative of velocity and you know how to use the calculator. So that's probably that's probably off an AP test, off the calculator form. So there's my velocity. I want the derivative. And so I guess it is a little bit weird. It's like, well, how do I know where to type it in? You just type it in. You just start putting the number in at 3, or at 4 in this case. Yes, sir.
Can you remember what number 3 is asking?
Okay. Ooh, that's a good question. The maximum acceleration. So we want to maximize acceleration. It's weird. So let's maximum acceleration. Whose velocity is given by. Well, let's get the acceleration. So that would be the derivative of velocity. 3t squared minus 6t plus 12. I feel like the AP test does this a lot. They word questions that force you into higher order derivatives. That, I mean, they're not hard to do, but you understand that if we want to maximize acceleration, then what do I need to do with acceleration? Like the last unit, when we wanted to optimize something, maximize or minimize it, what did we do first? I don't want to know where the acceleration is 0. I want to know where there's a max or a min. So I want to know where the derivative is equal to 0. So I need the derivative of acceleration now, which actually does have a name, but we don't worry about its name because it's a funny name. Tell us what its name is. What's the derivative of acceleration called? A jerk. Which, that actually has meaning, right? Like if you're accelerating in your car, you feel a smooth acceleration, you feel pushed against your seat, or leaning into your seat belt maybe if you're stopping. But if you change accelerations, what does that feel like in the car? It feels like a jerk. So that's side note, but that is what the derivative of acceleration is called. So we set that equal to 0. So at t equals 1, we think there's a maximum, but on this interval. So I don't know if that's a maximum or not. That might be a minimum. So how do I figure out if that's a max or a min? There's sort of 2 answers to this. If what's positive or negative? Right, the second derivative of acceleration. So that's like the 4th derivative of position, but whatever. The second derivative of acceleration is 6. What's that mean? That means acceleration is concave up. That means t equals 1 is a minimum. Now, if I'd have really been paying attention, what's the shape of this acceleration? So forget the acceleration velocity. What's the shape of that graph? It's a parabola, an upward-facing parabola. So yeah, that's got a minimum. Okay, so t equals 1 is not what I want. Find the maximum acceleration. Oh, on this interval. So if it's not at the critical point for acceleration, where might it be? I got to check my endpoints. So I need a of 0, which should be 12, and a of 3, No calculator, but okay. 3 times 3 squared minus 6 times 3 plus 12. 27 minus 18 plus 12. 9 plus 12 is 21. So the maximum acceleration is 21. It happens at 3. And that was a weird one because we were down to the second derivative of acceleration. I don't know if that has a name or not. Snap? I think you're right. Oh, is that where it goes snap, crackle, pop? I don't know that those have any real world. Snap, maybe. If you change the jerk, it's a snap. I don't know. There's a... famous isn't the right word. T-shirt. With that written on it. The third derivative of position. That's the derivative of acceleration. That's don't be a jerk. You gotta be a super math nerd to wear that T-shirt. I probably qualify.